theorem has to say. The rational root theorem, let's just kind of read through this together and interpret this, and then I'll show you why this works the way it does. This is handy. If p of x is a polynomial function with integer coefficients, okay, so this only applies if everything we've dealt with has had integer coefficients, right? And if m divided by n is a zero of this function, then this has to be true. So in other words, then if p of m over n is equal to 0, right? That means it's a 0, agreed? Okay, meaning that if we evaluate the function at that value, it's going to give us back 0. It has to be that way. Let's remind ourselves real quick why it has to be that way. So if here's my function, and let's just say that right there is at, we'll say m over n is like 2/3. So that's at x equals 2/3. And if this is p of x, then doesn't p of 2/3 have to be 0? Why? Somebody justify that. How come? If that's an x-intercept, how come? How come the function has to equal 0 then? Well, that's okay. It ends up being a factor, sure. But what else?
Y 0.
Because y 0. That's the definition of an x-intercept, right? And so we know then also that if this is a 0, then there must be a factor associated with that, right? So what would that factor look like? How did we find our factors from x-intercepts? What was the formula that we always or the process we always ended up using? Like if we had an x-intercept at x equals 3, what was the corresponding factor? X minus 3. So then what's this factor going to be? X minus 2/3, but it's not convenient a lot of times to write these factors in terms of fractions. So how could we clear that fraction? How could we rewrite that? Okay, I could multiply by 3, right? And we'd end up with, if I multiply, really this is going to be a part of, let's just say this is a part of a bigger solution where we've got x plus 2 times x minus 1 times x minus 2/3 equals 0, if we've got this thing in factored form, right? Well, if I multiply each side through by 3, what's that going to do to the right side? It just stays 0. Right, everybody agree? So that's no big deal. On this side, though, if I multiply the 3 by this factor, right, because I only multiply things in pairs, I go ahead and multiply 3 times this factor, and then times the other 2 would still give us 0, right? But if I distribute the 3 through to this factor, what am I going to get? You already told me. 3x minus 2, and then out front we'd have x plus 2 and x minus 1. So that's what the factor would end up looking like if we clear the fractions, right? 3x minus 2. So all I'm reinforcing here is that if m over n is a 0 of p of x, well, another way of saying that is just like this, right? P of m over n equals 0. But that's nothing new. We haven't added anything new yet. Here's the part that's new. If we get this rational 0 of our polynomial, and m is the numerator and n represents the denominator, then this has to be true. M has to be a factor of the constant term, and n has to be a factor of the leading coefficient. That's weird, but that's the rational root theorem. Okay, where does that come from? Let's explore that a little bit. It's pretty easy to prove. Okay, so how could we prove that? Well, let's just say we have a third degree polynomial, right? And let's say that all of the factors are inconvenient. All of them are not, we don't have integer zeros. Let's say we have these fractional zeros. Well, what would that look like then? Maybe something like this. Each one of these would be of the form, we'll call the first one a sub 1 times x plus b sub 1. what would the 0 of that factor be? If I set it equal to 0 and solve. Yeah, and I'll tell you what, let me change this sign. I'm going to go ahead and, not that this really matters, but I'm going to change this to a minus. So now what would it be? B1 over A1. Okay, so we'd end up with the 0, x equals B sub 1 over A sub 1. Let's say we multiply that by A sub 2x minus B sub 2. So by the same logic, here we get the 0, x equals B sub 2 over A sub 2. And how about the one more? A sub 3 times x minus B sub 3. And all that's equal to 0. Right? Okay, so let's imagine that we expand this whole thing out. That would be a lot of work, right? But let's just look at what the leading coefficient and the constant would have to end up being, right, if we did that. So what if we multiply the first two factors, what's the leading coefficient of the first two factors going to be when I multiply those out? What's it going to be? No, if I'm multiplying these two together, I just want to know what's the leading term going to be? What's going to be the biggest power of x? X squared. What's going to be multiplied by x squared? See you guys. What's going to be multiplied by x squared? Okay, not a squared. It's going to be a sub 1 times a sub 2, right? Everybody agree? If I expand those out, when I distribute the a sub 1 times x to the a sub 2 times x, I'm just going to get a sub 1 times a sub 2 times x squared. Agreed? We're going to get another term in the middle that we don't really care about. But what's the constant going to look like? B sub 1 times B sub 2, right? Does that make sense? If I were to expand this out, then I'd get some x term in there that would involve a sub 1s and b sub 1s and a sub 2s and b. It might be complicated, but we don't care about that one. All we're going to focus on here is what's going to be the biggest, the leading term and the constant each time we multiply. So we're going to get first term a sub 1 a sub times a sub 2 times x squared. Constant's going to be b sub 1 times b sub 2 when we multiply those together, right? Now, what if we were going to multiply that one through, distribute that through by a sub 3x minus b sub 3. And let's just go ahead and distribute the a sub 3 backwards here. So if we distribute that back to the x squared term, that's going to give us the leading coefficient of our answer, isn't it, with the biggest power of x? Okay, what's that going to look like? Okay. A sub 1, a sub 2, a sub 3, x cubed. Right? Everybody agree? When we distribute this to the other terms, we're just going to get some lower powers of x that we don't care about. Right? When we distribute the negative b3 all the way through, and we distribute it to the first or the second terms, we're just going to get lower powers of x, less than x cubed, so we don't care about those. But our constant is going to end up being what? Yeah, so I'm going to get some stuff in the middle I don't care about, and then at the end I'm going to get a negative b sub 1, b sub 2, b sub 3, right? And all of that is going to equal 0. Okay. So let's look at the leading coefficient then of my expanded polynomial, right? Written in standard form. The leading coefficient is the product of a sub 1 times a sub 2 times a sub 3, right? Yes?
What do the little sub numbers mean?
Oh, they're just, the little sub numbers are just distinguishing, this is just first term, second term, third term. So a sub 1 is going to be some integer, b sub 1 is going to be some integer, but we put the 1s there just because that's going to be in the first factor, right? Okay, so then now look at what our, this is the leading coefficient, right? this is the constant. If I look at the zeros of each of those factors, what do you notice? Well, on the top, we've got some factor, either b sub 1 or b sub 2 or b sub 3, right? Those are factors of the constant of the overall polynomial then, aren't they? Everybody see that? Wouldn't you agree that b sub 1 is going to divide evenly into b sub 1 times b sub 2 times b sub 3? Right? For sure. And so is b sub 2, and so is b sub 3, because those are parts of that product, right? Look at the denominators. The denominators of each of these are just either going to be a sub 1 or a sub 2 or a sub 3. Well, obviously, those are factors of the leading coefficient, right? Yes?
So if we're going back to the original
Mhm.
things, then B would be N and A would be N?
Well, so, right. So B would be, so we had M over N. So like M in this case would stand for B sub 1 and N would stand for A sub 1 if we're looking at that zero, right? Or if we're looking at this zero, M would be B sub 3 and N would be A sub 3, right? Point being that anytime we've got a polynomial that's got integer factors or integer coefficients, right? If there is a rational zero, which would mean that the factor would have to look something like that, right? Right? Then has to, there's no way around it. The numerator has to be a factor of the constant, and the denominator has to be a factor of the leading coefficient because of the way this multiplied out, right? So then let's put that into practice. When you put it into practice, I think it gets a lot less mysterious. So let's take a problem like this. Okay, that looks kind of hard. If this has rational zeros, and I guess I should preface this by saying not all polynomials are going to have rational zeros. And if they don't have rational zeros, how valuable is the rational root theorem? Not very valuable. I guess the only thing it could tell you is that if you tried all the possibilities, you would just know there are no rational zeros. But beyond that, it doesn't really help you find the irrational zeros, right? So that's something that there is a technique for doing that in algebra, but it's such an ordeal that we're not going to do it because we'll learn techniques in calculus that are way easier, okay? But a lot of times there will be a rational zero. And so when there is, this is a great way to find it. I mean, where else would you go with this? This is one that would be really hard to do without the rational root theorem because you can see right away, can't you, that factoring by grouping is not going to work, right? If after doing those factoring by grouping problems, you kind of got a sense that the ratio of this coefficient over that coefficient would have to be the ratio of that one over that one, right, for factoring by grouping to work. And so this one wouldn't, and let's just show that real quick. What's the greatest common factor? If I try to group this thing, what's the greatest common factor of the first group? X squared, right? So we could factor out an x squared, leaving us with what?
4x minus 5.
Okay. Now what about over here? Well, there's no way I'm going to get a 4x minus 5 out of that, is there? Right. If I did group the second group, the best I could do would be to say negative 9 times what? X plus 2x plus 1. But I can't group that, right? There's no common factor in the groups. So factoring by grouping is a lost cause. You may be able to make factoring by grouping work, maybe with a lot of work, if you were to, for example, break up these two terms so you could make a trinomial plus another trinomial, but man, that's a lot of work. And it's not always successful, and so I'm not going to throw any of those at you and expect you to do that. It just seems like too much. And it's not a very good strategy anyway. But what could we do? We now have a new weapon in our arsenal. We have the rational root theorem, right? So what's the complexion of all the possible roots that we could addition? I mean, it would have to be, all of our roots would have to be of the form of some fraction where on the top we'd get all the factors of what? Of what?
B.
Well, what did we say if if we're gonna have a fractional zero, the numerator would have to be a factor of the constant, right? And the denominator would have to be a factor of the leading coefficient, right? So in this case, if we're gonna have zeros, zeros would have to look like factors of -9, right? So what would that be? Plus or minus 9, or plus or minus 3, or plus or minus 1, divided by, what could the denominator be? Yeah, plus or minus 4, plus or minus 2, plus or minus 1. Okay, so what's going to be the easiest case here? Where the denominator is what? 1, right? We'd like to try the integer cases first. It'd be harder for us to deal with fractions than it would than integers, right? And you can kind of see why when we go through the synthetic division to test these out. I'll kind of ask you again, why would the fractions be so much harder? Yes?
Are those possible numerators and denominators interchangeable with one another, or what would be 9/4?
No, it could be 9/2 or 9/1. It's just that the numerator has to be one of those. If it's rational, it has to be one of those factors, and the denominator has to be one of those factors, right? Okay, so let's try some out. What's the easiest one to try? Yeah. Yeah.
1/1.
Yeah, we'll just try. How about if we try? We're going to focus on the bottom being plus or minus 1. So we'll look at the integer values of the numerator then, right? So 9 over plus or minus 9/1, plus or minus 3/1, plus or minus 1/1. Those would be the easiest ones to addition. And if those don't work, then we'll move on to the fractional ones, right? But we're always going to try the integer possibilities first. So let's just set up a synthetic bracket, and here's all we have to do. So how about if we just try 1 first, right? What are my coefficients up here?
4, -5, -18,
So 4, -5, -18, -9. And if it's a 0, we gotta end up with 0 in there. Yeah, Jesse?
Would you get those numbers with x equals?
Because of the rational root theorem, right? Because the rational root theorem that says that if we get a fractional 0, a rational 0, then if that exists, then for sure the numerator has to be a factor of the constant, and the denominator has to be a factor of the leading coefficient. There could be no other possible fractional zeros. So in our case, the constant is 9, right? And the leading coefficient is 4, -9. It doesn't matter. We're going to try always positive or negative factors anyway, right? So we want all the possible factors of 9 over all the possible factors of 4, right? So for example, I mean, there'd be a lot of possibilities there, right? So we could get plus or minus 9, plus or minus 3, plus or minus 1. Or we could get plus or minus 9 halves, plus or minus 3 halves, or plus or minus 1 half. Or we could get plus or minus 9/4, or plus or minus 3/4, or plus or minus 1/4, right? So there's lots of possible candidates here. And we're just going to try to exhaust the easy ones first. We'll test the easy ones, because what happens to this thing, if we can just stumble on one of them that's an actual 0, what's going to happen when we divide that through? What are we going to be left with? It's cubic right now. It's going to, and so it'll be a quadratic trinomial, right? Then we're done. Just use the quadratic formula and we're finished, right? For the rest of them. So we just need to find one. If we can find one, this thing will break down into a much easier problem. So let's try these out and let's just see if we can find one. So what do we get here? I bring the 4 down. 1 times 4 is
4,
plus -5.
-1.
1 times, this is not going to work, is it? You can already see it's not going to work. So we'll cross, let's keep a list of the ones, well actually we'll just cross these off. So we'll cross off +1. So what could we try now? How about -1, right? Okay, and let's do the same thing. But what do we have to, over here, do we have to erase and start over? No, we don't have to do that. Let's just make a new line, right? We'll just make a new line and cross that off and cross that off. And let's make that a -1, right? And so I'll bring the 4 all the way down to here. Negative 1 times 4 is negative 5 and negative 4. Negative 1 times negative 9. Negative 18 plus 9. Negative 1 times negative 9. Negative 9 and 9. Got it. Okay. So we found one. So we know that negative 1 worked. There's 1, 0. Now we're done, right? From here on out, what does this leave us with? This leaves us with the smaller equation. What? What's this correspond to?
4 squared minus 9x.
Okay, and then we already had this one out front. We had this x minus negative 1. There's the other factor, if we want to write it, right? But we already have that 0. Now we just have to find these. So what are our options? Quadratic formula. You might just see real quick if magic numbers are you're going to work. You're going to find some bottoms up. So can you think of some numbers that multiply to negative 36 and add to negative 9? Yeah, negative 12 and positive 3, right? So we could do bottoms up, and that's probably going to end up being a little faster than quadratic formula. But quadratic formula would work, right? So if we do AC equals negative 36, B equals negative 9, that gives us the magic numbers negative 12 and positive 3, right? So we could break this down into x minus 12 times x minus 3, and what do I divide each of the constants by when we're doing bottoms up? 4. Yeah. So then what do those become when I go bottoms up? This is going to simplify to what? 3. And this one doesn't simplify. So what do I have to do here? 4x minus 3. So I'd end up with x minus 3 times 4x minus 3 times x plus 1. If I wanted to write it in factor form, but I don't really want to. All I really want to do here is just get the zeros, right? So we already had this one. X equals negative 1, x equals 3, and x equals what? 3/4? Okay? Yes, sir.
Shouldn't it be x plus 12 because it's x minus negative 12? Because if you look at the top right.
Oh, yeah, you're right. Yeah, it should be. Yeah, that's a negative 12. So then that would make that a plus 3. Yeah. Okay? Make sense? Okay, let's try another one. Okay, how about that? So this one, you look at this one and right away you say, whew, how come? Yeah, A is 1, right? And so of all the, let's look at all the possible factors we've got. So the only possible solutions are going to be of the form x equals all the positive and negative factors of 12 over the positive and negative factors of 1. Awesome. That means we would never have to deal with any fractions. If we go back to that last one, do you see why fractions would be a pain? Fractions would be a pain because if I had a fraction out here and I bring this number down, when I multiply by a fraction, I'm going to get another fraction, possibly, right? And then all of a sudden I'm adding and subtracting fractions and multiplying by fractions. And that just makes things harder, right? Dealing with fractions is just more complicated than dealing with integers, right? But here we're safe. If we can solve it, right? If they're going to be rational zeros, then they're going to be integers. So what are they going to look like? Okay, how am I going to write all the possible solutions we could get here? What would the possible numbers be on top?
Plus or minus 12, plus or minus 6,
Good.
plus or minus 4, plus or minus 3, plus or minus 2,
Wow, we get a lot, don't we?
plus or minus 1,
All over.
plus or minus 1.
Okay, so essentially we just get plus or minus 1, 2, 3, 4, 6, or 12. And so once again, we're just gonna, we gotta find, this time, we gotta maybe, it depends. If we find 1, then maybe grouping's gonna work, right? Maybe. We'll get this down to a point where if we get rid of 1, if we factor 1 out, this quartic becomes a cubic, right? And if it's a cubic, maybe it ends up being a cubic that's gonna be one that we can do without having, we can just solve algebraically. If so, we'll do that. If not, we'll just keep going, right? We'll keep additioning more, okay? So let's try this. Set up our synthetic bracket. Let's see, so our coefficients are 1, -9, 27, -31, 12. What do you want to try?
2.
Well, let's try the easy ones first. Let's try 1 and -1. Right, those are always the easiest. Yes, ma'am. Sure. Okay, so let's just try. How about try 1? So I bring down the 1. 1 times 1 is. What do I get here? -8. So I get 8. That's not going to work, is it?
-8 shouldn't it be negative?
Oh, yeah, you're right. -8. So let's see what's that give us. 19. That might work then, huh? -8, so that's going to give us, doesn't that give us, that does give us 19, right? So 1 times 19 is 19. -31 and 19 is what? 1 times -12.
12.
Okay, so, wow, that's great. We found one. That worked. Okay, so 1 was a solution. Now what do? Now we just come down here and we'll just do what I call nested synthetic division. We'll just start again, only now we got a smaller one to deal with, right? So now our bracket looks like that. Well, what should we try?
3.
We could. I'm going to say definitely try 1 again, because it could be a double root. And then if it doesn't work, we can cross it off the list. Does that make sense? Okay. So let's try 1. Bring down the 1. 1 times 1 is 1. -8 and 1 is -7. -7, I get 12. And what do you know? It worked again. Okay? So 1 was a double root. And now it's quadratic, right? In fact, you can see the magic numbers right there, can't you? They'd have to multiply to 12 and add to -7, wouldn't they? Everybody see that? So we can see right now that this is going to factor into, I'm left with x squared minus 7x plus 12. And so we're going to get x minus 3 times x minus 4. And so what are my other zeros? 3 and 4. So if we wrote the whole list of zeros out, what would they be?
304.
They'd be 1, 3, and 4. But if we read, let's go back and read if multiple zeros exist, separate them with commas, right? Because we got to keep track of all, and it's important if something's a double zero, right? So in this case, we'd write this out. If we're entering this in Moodle, we'd enter it in Moodle, like here to say, here's the Moodle box. We'd go 1, 1, what were the others, 3 and 4? 3, yeah. 3 and 4, any order. Does that make sense? Okay. We out of here in 1 minute. Oh man, I gotta take a roll. Shoot.